Good evening, everybody. Let's take a look at Lab 3. So Lab 3, it's about inference for categorical data. So far in class, we have talked about confidence interval and hypothesis testing for categorical data. We talked about proportion, but think about it. How did we get proportion? So if you have a categorical data with two categories, for example, yes or no, and often we're interested in the percentage or the proportion of people who said yes. So in this case, the proportion is computed from the categorical data. So far we only did the one sample proportion test, and tomorrow we're going to do more on those. And on Wednesday, Baharna would continue with two sample proportion test. And on Thursday and Friday, I would talk about the chi-square test. So I realized that the material, like the knowledge you need for this lab, are going to be taught this week. So I'm going to give you guys 2 more days. So this one will be due on Monday. And I will also send out an email about this, okay? So let's take a look at this data file. This one is actually really interesting. And it's quite different than the usual medical related or engineer related example we talked about in class. This one is about anthropology. Okay, so this one is called Donor Party Natural Selection in Action. So if you open Wikipedia, there is a whole page about what it is. So basically, I only read part of it. If you're interested, I think it's a really interesting story. So basically, in April 1847, there are 87 people who traveled from. So there are a group of American pioneers who migrated to California from the Midwest. Okay, so they were delayed by a series of mishaps, and they spent the winter of 1846 to 47 snowbound in Nevada. And a lot of them did not survive, and some of the migrants resorted to cannibalism to survive, eating the bodies of those who were dead to starvation and sickness. So basically, 40 out of 87 did not make it. Okay. So the data on the survivorship of the party member may be used to gain some insight into human behavior and natural selection under extreme cases. Okay, and I believe the people who are traveling are mostly two families and their servants. Okay, again, I might be wrong. Should read more about this. It's really interesting, actually. So I think it was two family, Donner and Reed. So Donner Reed party. So for the data we have a bunch of variables. So we have the name, the full name of the passenger. We have the gender. We have the family name, so which family it belongs to. So based on this, it seems there are a bunch of different families. There's Donner, there's Breen, there's Casper, and Murphy, and blah blah, a bunch of different families. And we have the position. So position indicates the member status within the family. So we have the Teamster, son, father, mother, daughter, and hired, so husband and wife. And then we have the age, the estimated age as of July 31st, April 1846. So this is about a year. So this is the age when they left for the travel, for the migration. Okay, so we have some really young, like there's a baby here, and there's someone who's as old as 61, and there is the child variable to indicate whether this person is a child or not. We have the survival outcome, whether the person made the trip or not. We have the order of death. Okay, so see, some of these, the variable order is missing. So missing means what? Means this person survived. so there's no order of death here. And the one who was dead here has an order of death. So, and I assume the smaller the number it is, it means it died earlier. Okay. And then we have the variable alone. So alone means whether the person is traveling alone, so no family, no close accompanying person, and then we have the group size. So group size indicate the number of group members. Okay. So again, the data I'm using, it's similar to yours, but what I did is, first, initially I want to change the number, but I feel like I would be changing the history if I'm changing the number. So what I did is I only selected a subset of the data. So you have 87 observations, and I randomly selected 70 of them, okay? So the numbers I'm getting will be slightly different than yours. Okay, let's take a look. So it's pretty interesting, I would say. See, so we have the kind of the outcome is whether survived or not, and we have a few demographic information about these people. So we can take a look to see whether we can find any of these variables that are related to survival, like, whether adults are easier to survive, whether adults are more likely to survive than children. Things also like whether the same family like to stick together and they all survive, or maybe the women or the men have a larger chance to survive, and also people who are older or younger who are more likely to survive. So we can do all kinds of comparison. As you can see, why this data is very suitable for inference for categorical data, because we're talking about proportion, right? And then in this case, we can talk about the proportion of female who died, proportion of male who died, and we can do the comparisons. Okay, so before we jump into the analysis, let's take a look at the design information. How did we collect the data? So first, is this observational study or randomized experiment? So again, the two keywords here, observational versus randomized, depends on whether you have manipulated the treatment. In this case, it's hard to say what is the treatment. I mean, if you say whether the person survived or not, because apparently that's the variable we are interested in, it's the variable, then obviously we cannot, and any of these information here, we cannot manipulate. You cannot manipulate people's age, whether this person is a child, whether this person travels alone, and again, all of this is history. All of this happened, and we recorded data. We are someone who, we have no control on the history. This already happened, so very clearly, this is an observational study. And I assume for all anthropology, maybe not all maybe 99.9% of anthropology study, you can't do experiment, because what you're supposed to do is to study what has happened, without people touching this or touching that, if that makes sense. And then it asks you about generalization. So whether this can be generalized to a broader population. So the sample we have is the 87 people, or the 70 in my case, 87 people who were traveling from Illinois to California. And from the sample to the population, and then you have to ask yourself, what is your population? Which population you want to generalize into? So that's the first question. It's hard because, I mean, if you're saying I want to generalize this to all people who are traveling from Illinois to California at around that time, if that's your interest, then no, because again, generalization or not depends whether you have a simple random sample from your population. So these people, they are not randomly selected. They just went there. It's not like we have a pool of people who wants to go to California and we select some of them to do this experiment. Again, we have no control over this. Okay. And then ask you, for example, if we found out females are more apt to survive than males, can we use this as a proof that in general females are better than males to withstand harsh conditions? So this one is kind of asking about causal inference. Like, for example, if you find out the survival rate for females higher, can you conclude that this is because of the gender differences? And again, the key to the question is whether you have a randomized experiment. So in this case, we only have an observation study. The thing for observational study is there are so many possible confounding variables. For example, if you found out females are more have a higher survival rate, there could be a million other reasons that cause this instead of being a female. So what's a good reason here? For example, I don't know, maybe the men are in charge of getting people out of the snow, so the man would consume more energy, if this is correct. But as you can see, there could be many theories to explain why the females have a higher survival rate. So no, we cannot use this to conclude that the higher survival rate is caused by gender. Okay. And now let's take a look at the data. So how many cases there are? So apparently you have 87. I only have 70. Identify categorical and numerical variables in the data. Noting which one is the identifier variable. So this is easy, right? I think the only continuous variable, the quantity variable we have is age. We have the group size, which you can treat this as quantitative, I think, because even though we have only a few categories, but the number here actually makes sense. Like it has a unit. Group size equals 1 means one person in this group. Order here is apparently an ordinal variable, but this ordinal variable has so many levels. You can almost treat this as continuous. That makes sense. But also for order, it's special because we don't have order for the survivors. Okay. And identifier. So identifier variable means something that's unique. So here name is unique. Okay. I assume nobody has two same names. Oh, maybe it does. See, we have. Oh, I thought we have lots of Elizabeths. I guess it's different. Eliza, Aletha, Elizabeth. It's a popular name. Okay. Now let's do some simple analysis, some simple frequency table to get some summary statistics. Okay. So question 3 asks you to use frequency table to summarize the family and gender composition of the group and obtain the proportion of group members who survived for each family and gender. Let's take a look at each question one by one. So first one, what's the overall survival rate? Obtain frequency table, include frequency and relative frequency. So in this case, we just need a frequency table. So let's go to statistics, tables. Where is tables? Tables, okay. Oh my god. Frequency table, survival. So survival. In this case, we're looking for the overall survival rate. So let's just leave this. And we need both frequency and relative frequency to compute. So based on this, so there is about, in my case, again, your data is different. I have a 52% survival rate. Okay. So 3b asks which three families proportionally lost more members proportionally. Obtain the frequency table. So see, this one is asking for proportionally, so a relative frequency would be more appropriate, I would say. But let's include both of them, okay? So in this case, we need to do the statistics table, frequency table. We are only also using the survival, okay? But we're going to group by the family because we want to compare the survival rate for different families, okay? Let's do compute, okay? Oh, let's go back to see if I can order this easier. Maybe let's order by count descending. Does it make more sense? Oh, this is just from, I guess we have to look at this one by one. So lost more. So lost more means survival rate is low. So for the Donner family, the survival rate is 45%, and we have 50% for Graves. Murphy, 55%. Reed, 66% survival rate. Green, 85%. Oh, this family, Casberg has a really low survival rate, so 80% died. So this one too, and I mean for this one it's just kind of hard. It doesn't have any because you only have one eddy, so it lost its statistical meaning. So if I want to compare, I want to say again, you can order this by the died rate, okay, but also be careful when you have a case like this. You can mention it, but also point out that there's only one person in this family, okay. So do the comparisons and get the top three. Or 3C asks about the survival rate for people who are traveling alone and what was the survival rate of people who were not. So we're gonna do traveling alone. Traveling alone, we have a variable alone, yes. So similarly, we're gonna do the frequency table again. Frequency table again. So again, we care about survival, but in this case, we're gonna group by alone, okay? So compute. So for the people who travel alone, there is 80% of 80% of, how do I call it, non-survival rate? I mean, I'm just going to talk about survival rate. 20% of survival rate, very low. For people who are traveling with somebody, 61%. As you can see, in this case, as you can see, you don't need to do any statistical analysis. You can just look at the table. You can see that traveling alone or not has a huge impact on your survival rate. If you're traveling alone, you have a much higher chance of dying. Okay. That's a good lesson. Okay. That's 3C. Okay, and then 3D asked for gender. So again, we're doing the similar thing, relative bar chart. It also asks for bar charts separate for each gender. So let's do the frequency table first. Frequency table, and then we're gonna do survival by gender. Okay. So for female, there is a 75%. A male, there is only 36%. See, big difference. This is a big difference. For the bar chart, is it bar chart or pie chart? Bar chart. Graph, bar chart with data. And then let's do survival, group by gender, grouping options, separate graph. I think the question asks for a separate graph. Did it? Yes. Frequency, or it asks for relative frequency. Relative frequency. Okay. Let's do this. So I have first female bar chart. So lots of them survived, and then this is more than 50% of them died for male. See, big difference. 3E was survival rate of children, survival rate of adults. So again, in this case, we again care about survival rate. We're going to do the frequency table again, but in this case, we're going to do the by option using child. Okay, so statistics table, frequency table, survival, group by child. Hopefully, child have a higher survival rate. No. So the children has only 34% survival rate, and the adults, oh no, yes, no, the adults, the child equals to no means adults, so adults have a 34% of survival rate, children have a 71%, so kind of makes sense. The parents must be protecting their children. Yes. F is looking for summary statistics of age for survivor, non-survivor separately, and then the box plot. Okay, so let's first do the summary statistics. So statistics, summary statistics, columns, age, and they're gonna by survival or not. Let's look at this. Okay, so for the survivor, the mean age is significantly smaller than, see, as we just saw, the children has a higher survival rate. So of course, the average age for survivors is lower for the non-survivors. Similarly, for the medium, it's also smaller, and we have 1 to 51. So the oldest survivor is 51 years old, and the oldest non-survivor is 61 years old. Okay, and let's do the box plot. So graph box plot, and then let's do age, group by survivor, survival, compute. So yeah, so you can see the box plot is much more straightforward than some of the statistics, as you can see. So we have, in average, the survivor is younger, but the range for the non-survivor is pretty large too, from 0 to 61. We have two outliers here. Okay. G is about summary statistics of age for survivors for each gender. Okay, so what's the difference? Oh, this one is looking for survivor, and this one is looking for survivors and non-survivors for each gender. Okay, so let's do statistics, summary statistics, columns, age, group by, this is kind of for survivors and non-survivors. Okay, but for where, we can choose, for example, if we first focus on female, so gender, so where we say gender equals to female. Okay, then let's do let's do compute. So for the gender equals to female. So for female, I have survivor is younger, so 15 versus 22. Similarly, we can do this for male. So edit, we change this to female equals to male. Then we do compute. So for male, similar pattern. So yeah. And that's it. Okay, that's for G. What's the difference in the average age of those who survived for each gender? Average. So again, think about which measurement you should use for average here. But in this case, I guess the mean and median are pretty close. Yeah. Okay, so in 4, it asks you to examine the relationship between survivor and gender. So survivor and gender. So we're testing for gender differences. What's the chance of survival different for male than for female? To answer the question, let's do a contingency table. Because for contingency table, if you put one factor as survivor or not another factor as gender, we can see whether these two variables are independent or not, right? Remember, we talked a little bit about this. Let's see, how do we do it? So if we go into statistics table, contingency table with data, and we put row variable as survival and the column variable as the gender, and then select row percent, column percent, percent of total, as well as a chi-square test. So chi-square test, we're going to talk about this on Thursday, okay? So here, as you can see, if you look at, so this is if we focus on the first column, okay, then this is the conditional distribution of survival for female. The second column is the conditional distribution of survival for male. And you can see the distribution is different because for the female, there is 75% who survived. For male, only 36%, a big difference. And if you look at the chi-square test, so what chi-square test is testing whether there's any relationship between gender and survival. So basically means this gender here matters when we are talking about survival rate. And we have a p-value, very, very small. If this means, okay, I'm going to continue. So basically for the chi-square test, oh, that makes sense. Okay, so for the chi-square test for independence, we will talk more on Thursday, but if you It was basically saying that the null hypothesis, again, the first step of hypothesis testing is to formulate your hypothesis. So the first null hypothesis, we say there was no relationship between survival, gender. And what's the opposite side of that? The opposite side, we said, again, this depends on what it is asking. It says survival rate different. So the keyword is different. So we're looking for two-sided alternative. If here it says survival rate higher for female, then we'll be looking for one-sided, okay? So the alternative would be there was some relationship between survival and gender. Okay, and then we have a p-value. I have a p-value of 0.0015. 12 or 15? For mine is 12, which is smaller than 0.05. So we're going to reject h 0. Reject h 0 means what? Means we have enough evidence to say that there is some relationship between survival and gender. Okay. And that should probably answer the 4b. Oh, it also asks for what's the distribution. So the distribution here will be a chi-square distribution. Chi-square distribution with degree of freedom. With degree of freedom, row minus 1 times columns 2, I think 1. Yeah. Again, we will talk more about this on Thursday. And if you look at the formula sheet, you will see the degree of freedom here is number of rows minus 1 times the number of columns minus 1. Okay, so in this case I have 2 minus 1, 1 times 2 minus 1 times 1 plus 1. Okay. And why is that chi-square distribution? Because we're doing a chi-square test. So whenever they ask you what's the distribution of test statistics, depending on what test you're doing. If you're doing a z-test, the distribution will be a normal distribution. If you're doing a t-test, it will be a t-distribution. Okay. So 4c says refer to the output in A, what percent of survivors are female? So see, what percent of survivors were female? So we're looking for a conditional probability, what percent of survivors. So we're only focusing on survivors. So P given survivors, what percent of them are female? See, this is different than P survivor given female. So we're looking for probability of survivors, so only focusing on survivor, only the second row. How many? 60% of them are female, about 40% of them are male. Okay. D says using alpha equals to 5%, is there any evidence that there is a difference in survival rate for female and male? For example, if I'm using P subscript F, or you can using P1, maybe I'm using PF to refers to the survival rate, oh my god, I'm so bad, survival rate for females. And I'm using PM for survival rate for male. Oh my god, I can't type this word. And then here it says whether there's a difference using the two sample proportion test. So two sample proportion test will be covered on Wednesday. So for two proportion test, it's similar to one proportion. One proportion we're comparing the P whether some value, like for example, if you're testing whether the coin is fair, we're comparing P equals to 0.5 or not. For two sample proportion, it's even easier. You're comparing two proportion. So in this case, the null hypothesis would be the female proportion equals to the male proportion. So this means what? This means the survival rate is the same for female and male, and the alternative is two-sided because the keyword here is if there was a difference. So we only want to know whether there's any difference or not. We don't care whether it's female has a higher survival rate or male has a higher survival rate. So the alternative is doesn't equal 2. So here it means doesn't equal 2. Okay. So that's the alternative hypothesis, and then let's do the test. So in order to do the proportion test, let's go to statistics, proportion statistics to sample with data. So the first sample is what this is female. So female survival rate, right? So values in survival. Success, if we define success to be survived, so we are comparing survival rate. If you put success as died, then we are comparing non-survival rate. Where, so the first one is female, right? So gender equals to female. Sample 2 is also survival, and success is also survived. We are comparing male, so female versus male. So this is hypothesis testing, okay? The non-hypothesis, the alternative two-sided, okay? And then let's do compute. So here it asks for a bunch of things. So first, what's the test statistics? So the test statistics is the Z statistic here. So Z stat is the test statistics. The distribution, so the distribution is a normal distribution because we are doing a Z test. The p-value is 0.0012. What do you find? The p-value is identical to the chi-square test. Okay. And so that's why based on this p-value is smaller than 5%, so our conclusion would be we are going to reject the non-hypothesis, reject this. Reject this means what? Means there is some difference between the survival rate between female and male, which is the same conclusion we got from the chi-square test. So that's why 4E asks you about the relationship between B and D, and you would see that the p-value is the same. The conclusion is the same, and in class we will talk more about this. When you have a chi-square test with only 2 categories for each row and column, it's identical to a true proportion test. So they're identical in this case. Okay. For 5F asked for a confidence interval. So it's the same procedure. If we go back, options, instead of doing hypothesis testing, we can do a confidence interval. For confidence interval, the question asks for 95%. That's the default. And if we do compute, so here the lower limit and to upper limit is the confidence interval. As you can see, the confidence interval is from 17% to 60%. And the confidence interval is positive. Positive meaning what? Here we're looking for P1 minus P2 means female minus male. Female minus male is always positive, means female is always bigger than male, means female have a higher survival rate. This is similar to the conclusion we got in the hypothesis testing, we only know there is difference, but from the confidence interval, you can see the sign. We know that female has higher survival rate. Okay, that's 4. It's pretty long, but hopefully you get it. Let's take a look at 5. 5 says we're going to explore the relationship between age and survival. First, divide age into several non-overlapping intervals so that the age of each member falls into exactly one of those. In order to do that, obtain a bin column, bin age. Make sure the left end. Okay, I have no idea how to do this. Let's take a look. We are splitting age. So I'm assuming we're going to data. Oh, bin. Okay. Bin of age using fixed starting at 1 and bin width was, this is kind of like a making a histogram. So we are, because age is continuous. When you have continuous variables, it's very hard to make a continuous table because your continuous table would have possibly infinitely many columns. So what do? We put people, have similar age into a group. Like in this case, we can put people who are from 1 to 6 as one group, 7 to 12 as one group, etc., etc. So you have less categories, okay? And the question says to include left endpoint. So include left endpoint. Compute. So we have a new column, which is got the bin H, okay, and then we're going to do a contingency table, so similar as 4. So now instead of doing gender, we're using this bin H. So let's do statistics tables, contingency table with data, the row being bin H, and then column being survival. Then we're going to select row percent, column percent of total, and then we're going to do the chi-square test, and then let's do compute. So, okay, so what's the two intervals that has the highest and lowest? Okay, so the highest, again, it's kind of a long comparison. The highest survival rate here, for example, I have survival rate for the 100% here, see? So my 7 to 13 has 100% survival rate. That's really high. And what's really low? Here is really low, 43 to 40 and 0%. But again, it's only 2% in this group. And I have a bunch of 0% here. Okay. Ignoring interval less than 5. Okay, ignoring less than 5. This one's pretty low. No, this one 21% is pretty low. Oh, you can go through this. It's so much work. 5b is asking to test whether we have any relationship between survival and age category. So again, we're doing a chi-square test. So the null hypothesis is that there is no relationship between age and survival, and the alternative is that there is some relationship. Using 1%, so alpha is 1%. Our p-value is 0.005, really small. So p-value smaller than alpha means we're going to reject null hypothesis. So reject null hypothesis means there is some relationship between survival and the age group. Okay, that's 5. So 6, we're going to do the similar thing, but we're going to do this between age, survival, and group size. So let's do this again. So statistics table, contingency table with data, and then we're going to do row being the group size, and then column being the survival. Then we do the same thing, row percent, column percent of total, and chi-square test. Let's do compute. So again, the highest survival rate. So the highest survival rate I have is 20%, 100%, but this one is really small group size. This one 100% with 4 group member, 100%. So this one is 9 group member. The lowest is 20% here is pretty low. Do I have anything lower than that? No. So my lowest survival rate group is the one who travels alone. That's not surprising. And they ask you the group size with lowest consists of what gender? Okay, the survival rate increase with group size. So what gender? So now the question becomes whether the person who are traveling alone are male or female. What's the gender distribution? So in order to find that, what you can do is you can use the data and row selection where you can select that the group size equals to 1. This means we're selecting the traveler, the lone wolves, or whatever you call it. And we have 15 of them. Let's take a look at the gender. Oh, so we have male, 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 male. I think all of them are male. Yeah, that's not surprising. So no female were traveling alone. That says something. And to remind you, the person who are traveling alone has the lowest of survival rate out of all group size group. And for the 6b, the null hypothesis, I think we found out that continuous zero group size. The p-value is actually larger than 1%. See, this is 1%. The p-value is larger than 1%, so we are not rejecting the null hypothesis. But you can notice that this p-value is very close to 1%. So even though we're not rejecting, but there must be some evidence there because the p-value is pretty close to 1%. Okay. So again, in reality, it's never black and white. So even though we are not rejecting, but when you're reporting this p-value, people would have some idea that even though the evidence is not strong enough, but there must be some relationship between the size, the group size and survival. Okay. And the last one, it asks you to briefly summarize the study. So briefly, okay. So which factor out of them, I'll leave you to this. So we have investigated a bunch of factors like gender, group size, whether the person is traveling alone, and we have age group. And then you can comment on, which factor you think is the most important ones when you're predicting survival. For example, if you're looking at a person here, a person out of the whole group, and you want to predict whether this person survived or not, which value would be looking at? I will be looking at whether they're traveling alone, whether he is a he or she, whether as a child or not, so things like this. Okay. And I'll leave you to that. And this is kind of an open question. And there is some evidence here, but there's some room for interpretation. So yeah. Okay, that's everything. This one is pretty long. It's actually really interesting. Actually, I found the data we haven't analyzed many other things. Like we haven't analyzed position, like whether the parents are most likely to survive, and you can explore that. So yeah, a few things we have talked about here, like chi-square test and two proportion test, we haven't done in class, but it will be taught soon. And again, this one will be due on Monday. I'll give you guys 2 more extra days, okay? So yeah, have fun.